Hello AP Chemistry and welcome to 15.7, which you might be like, ooh, end of chapter 15. But this unit still contains some of chapter 17, so don't get too excited just yet. All right, so first of all, Le Chatelier's principle, right, is really a qualitative way to assess what we already talked about with Q, right? Q gives us a quantitative, here is where we are, K is where we're going, right? Here, what we're talking about first, note that the one key criterion is that the system must be at equilibrium, right? So you will only ever use Le Chat's principle, right, as part of your discussion, right, if the system is already at equilibrium, okay? Note, that's very important, right? Now, this works because K is constant, right? K is constant at given temperature. Bear that in mind, right? K is constant at a given temperature. Therefore, we know that the system is always going to head back toward K no matter what stress is imposed on the system. So we can change the concentration and predict what a system will do. We can change the pressure, which is akin to changing the concentration, and we can predict what a system will do, right? We can even change the temperature and predict what the system will do and what effect it will have on K, because again, K is temperature dependent, right? So let's talk about those a little bit more specifically, right? So first, let's talk about the effect of changing concentration, right? Which, if we're talking about a gaseous system, would mean also increasing the partial pressure of something, right? So here we have this system, right? Where we have, again, the production of ammonia from nitrogen and hydrogen, right? We have initial equilibrium, because again, that's one of the key criteria, right? And then we add some H2, meaning we increase the concentration of one of the reactants. If we do that, right, then what that means is that the system is going to course correct, right? It's going to then head back towards K, which means it's going to consume reactant and make product, right? That's what it's got to do in order to go back towards K, right? So you'll see that in the graph, right, we initially have this bump because we added that, right? But then it goes down because we consume that, right? The nitrogen also has to go down because we consume the nitrogen in conjunction with the hydrogen, right? And we produce a little bit of this, right? And we establish new equilibrium positions, right? But the ratio of each of those new things is still going to be equal to whatever K is, right? Where K is equal to, right, our NH3 squared over our H2 cubed and N2, right? So what that relationship is unchanged, right? But our actual numerical values that go in there will be different than they were before. Yes, does that make sense, right? Which you can see from the graph, right? Yes? Okay. Note that the N2 will be lower than it was before because we consumed some, right? H2, even though we consumed it, will be higher because that's what we added. Yes? All right. Now, note that industrial chemists, right, so chemical engineers, right, can take advantage of this concept, right, in terms of maximizing yield, right? Because obviously if companies spend money to buy reactants, the goal is to get as much product as possible out, right? And we said in order to reach equilibrium, way back in 15.1, right, we said that in order to reach equilibrium, all species must be present. Yes, in order to reach equilibrium, all species must be present. But we can also take advantage of that by saying, what happens if we remove this, right? Let's say that we would constantly remove NH3 as it is produced. If we are constantly removing NH3 as it's produced, what is the effect? Right. If we constantly remove this, then the system will constantly go forward. Yes? If we remove NH3 as it is produced, the system will constantly move forward, completely consuming the N2 and the H2 in an effort to reach equilibrium, which it cannot because we don't have any NH3 present, right? And so basically this giant schematic from your guys' book is just showing you how, right, industrial engineers, right, so chemical engineers take advantage of that, take advantage of these chemical principles of equilibrium, right, of there being a K value, right? And how can we take advantage of that to maximize the production of ammonia, right? Which is one of those super important chemicals, right, in the world, right? In terms of making sure we have enough fertilizer, right, to grow all the crops that we grow, right? So yes, equilibrium. So Le Chat as it applies to gas phase systems, right? So first thing to notice is that these are gas phase systems, right? And when we have a gas phase system, one of the changes that we can do is to increase the volume of the vessel, right? So note that that part's important. We're specifically saying we increase the volume of the vessel. So we can either, so it's got like a plunger, for example, or a piston where we can increase the amount of space that the gas has access to, or something like that, right? So we increase the volume of the vessel, which decreases our total pressure, right? And if we decrease our total pressure for a system that is at equilibrium, right, because that's the key thing that must be true in order to apply Shatley's principle, right? So if we increase the vessel volume, which decreases the total pressure, the system will shift to increase the total pressure, right? Because the system wants to go back to where it was. And in order to increase the total pressure, it's going to go to the side that makes more moles of gas. Yes? Because more moles of gas means more collisions with the walls of the vessel and an increase in the total pressure, right? On the flip side, right, if we decrease the volume of the vessel, it increases the total pressure. And if we increase the total pressure, then the system wants to decrease, right? And it'll go to the side with fewer moles of gas because that will be less collisions with the walls of the vessel, right? And a decreased pressure, which sends us back to where it was before, right? Now, like we said previously, right, all of this is a qualitative discussion, right? Where we talk just about if the pressure changes, right, or if the volume changes, then the pressure changes and this is what happens, right? But we could also look at this as a Q versus K because it just depends on what's being asked of us in the question and what we're trying to do, right? So if we think about increasing the volume of the vessel, first let's get a K expression, right? So K is equal to, broadly, let's use the reaction we're given, right, which is B partial pressure of B over the partial pressure of A. This one is squared, right? So here is our K expression, right? So then if we plug in some random numbers just to make sense of it, right? Well, first, the key thing here is that this part is squared, right? All of this discussion is pointless if the coefficients are the same, right? Does that make sense, right? If A and B, or product and reactant, had the same coefficient, nothing would change, right? Does that make sense? Because neither side produces more moles of gas, right? But because in this case, right, we have that 2, that affects what happens when we change, right? So let's say, for example, if I were to go under this direction, right, which is increase the volume and decrease my pressures, right? If I decrease my pressures and I think about the outsized impact that has because of the squared in the denominator, what happens to Q? Right, Q is greater than K if I increase the volume of my vessel, which decreases the partial pressures of my respective gases, right? And if you're not sure about that, we can plug in some pretend numbers, right? So let's say that the pressure of B initially was 2 and the pressure of A initially was 4, right? So 2 over 4 squared, right? Versus if I decrease the pressures, which would give me 1 over 2 squared, right? So I go from 1/16 to 1/4, right? Q is greater than K if I increase the vessel volume, right, which decreases the partial pressures. And if Q is greater than K, what does the system do? Right, if Q is greater than K, we consume product and produce reactant, right, which is the exact same thing that we predict via Le Chat's principle. And opposite on the flip side. Yes, does that make sense, right? So always, right, Q or Le Chatelier's principle, right? Either one is going to be acceptable unless the question prompts you to give one type of answer or analysis, right? Okay, now let's move on to the next section. Heat, right? So let's talk about if we change the temperature, right? So first let's talk about and make sure that we are crystal clear on endo versus exo, right? So if I have a reaction, right? So here I have, let's say I have, if I have reactant and product, right? And this is an endo process, right? Heat is like a reactant, right? For an endo process. If I have an exo process, here is my reactant, here is my product, then heat is like a product. Yes, as in heat comes out and in an endo, heat goes in, right? And so if we think about that, we can treat it like, and we would use the word like there because it isn't actually, right? So we can say heat is like a reactant in an endo process. Heat is like a product in an exo process, right? And that's how we can use, that's the wording we can use to justify our answers, right? So if we look at this example given to us, right, we have a endothermic reaction, right? Where heat is like a reactant, right? And here we have a system that is at equilibrium, which is essentially purple, right? Because we have both blue and pink, right? Present, right? And if we add heat, we go forward, right? Because it's like adding a reactant, so the system shifts to consume the reactant and produce product, right? Which happens to be blue, right? If we cool the system, right? Cool means to remove heat, right? That's what that means, which in this case is like a reactant. So if I remove a reactant, then the system will consume product to produce more reactant. Thus, we end up on the pink side. Yes? Okay. And so what that means is we can talk about heat in that way, right? We can also talk about what changes will occur, right? So first, if I say that heat in this direction, right? So if I add heat, which is like a reactant, the reaction will go forward, right? Producing more product means we have an increase of K, yes? As in that is a new permanent change, right, in the equilibrium point. My K is going to be bigger because I've made more product and I've changed the equilibrium constant in that way, right? Okay, so then if I talk about it from the perspective of cooling, right? So if I'm cooling, what that's doing, again, is that I am removing heat, right? So the system is going to shift to produce reactant. And by producing reactant, right, I am going to decrease my K value. Yes, does that make sense, right? So here I can say heat is like a reactant or product and justify which direction the reaction is going to go. But then based on whether there is more product or more reactant present, I can also say what's going to happen to my new K value. And every time we talk about temperature changes, we have to include what happens to K. All right. Finally, this section closes with a look at catalysts and what catalysts do, right? So we talked a little bit about them in chapter 14, right? In terms of this anyway, right? We said that when we add a catalyst, right, it is a lower activation energy because it provides an alternative mechanism, right? And so the reaction happens faster, right? Which means if the reaction happens faster, right, so it has a faster rate, what that means is it reaches equilibrium sooner. So if we look at this graph of concentration versus time, right, we will see this marks our equilibrium point, right, where the concentrations are no longer changing, or, well, for this green line anyway, right? Whereas over here, we don't reach equilibrium till maybe here, right, on the purple, right? So what we're saying is that looking at the green line, which is catalyzed, right? Catalyst, right? If we look at that green line, we reach equilibrium in a shorter amount of time, right, than we did without a catalyst, yes? But we reach the same equilibrium point, right? Does that make sense, right? We still hit the same max amount of stuff. We just do it at an earlier time on the x-axis. Yes? All right. Thank you for listening. Be good, and I will see you soon for Chapter 17.